Section 3.7 is the final section of Chapter 3, graphing absolute value functions. So in Section 7, we kind of move away from linear functions for a while, and we talk about absolute value functions. Absolute value function is a vocabulary term. It's simply a function that contains an absolute value expression. Now remember, absolute value expressions are the vertical bars around things. And remember, absolute value is a distance away from zero. And absolute value functions are their own separate family of functions. Remember, we talked about families of functions in Section 6. We talked about lines. That's a family of functions. Another family would be absolute value functions. And the parent function of the absolute value functions is f of x is equal to the absolute value of x. So let's think about what the graph of the parent function would look like. So if we have x and y, remember y is the same thing as f of x. So we could rewrite this as y equals the absolute value of x, not 1 times 1, absolute value of x. Okay. When I choose my x values to graph something, I like -2, -1, 0, 1, and 2. Kind of the center of the graph allows me to see everything. Okay. So if I were to plug in these 5 x values into this function here, really what we're figuring out is how far away are each of these points away from 0. So if we think about 0, how far away is 0 away from 0? That would be 0 units. The x value of 1 is 1 unit away from 0. The x value of 2 is 2 units away from 0. The x value of -1 is also 1 unit away. Remember, absolute value cannot be negative. Absolute value is a distance from 0, and it's not possible to have a negative distance. Okay, and then the absolute value of -2 is +2. All right, so we have our x and y values. So let's take a look at the graph of an absolute value function. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so let's plot these points. We got 0, 0 is right here on the graph. 1, 1 is there. 2, 2 is there. -1, 1 is there. -2, 2 is there. So this one is not a line. It makes a V shape, and it's a very distinct V. It makes a point. Okay, and that point is a special point. This point right here has a specific name, and that name is the vertex. It's the point where the graph changes direction. So here we can see, it's going downwards, and then it turns around and turns back up. Okay, so every absolute value function has a vertex. Okay. And that's kind of an important part, because usually when I make my table, I try to keep the vertex in the middle. In the parent function, the vertex is at 0, 0. It's the point where it changes direction. And you can see it in the y values. Goes down, hits the bottom point, and then turns back upwards. Okay? So let's think about doing some more. Let's graph a few more. But before we do that, we need to do a little bit of review. If you remember from Section 6, we talked about translating graphs. Remember that if we add something to the original function, that's a vertical change. And if we subtract or add something directly from x, that's a horizontal change. Okay, it's a horizontal translation. So number 1 here, graph the function compared to f of x is equal to the absolute value of x. Describe the domain and range. We have several things we need to do here. Let's actually start with compare to f of x is equal to the absolute value of x. Okay, remember what we've done in Section 6, we replaced this with f of x. Okay, so we could think of it as f of x plus 3. Obviously, the plus 3 is not on the inside of the parentheses or inside of the bracket. This is an outside, which makes it a vertical change. And since it's adding and subtracting, this would be a translation. Translation 3 units. And since it's vertical, the directions are normal, that would be a direction of up. So it's a translation 3 units up. That's the comparison to the original function. F of x is equal to the absolute value of x. Okay, so let me get rid of the red writing. Okay, so the first part, compare the f of x to the absolute value of x to the original, or the one we're given. It's a translation 3 units up. So graph the function. We'll do that in purple here. Okay, so what I'm going to do, so if I think about my parent function, okay, my x value is -2, -1, 0, 1, and 2. Okay, we know what the original one, we know what the absolute values of these are. All we have to do is add 3 to both of them, to all of them. Okay, so the absolute value of 0 was 0, and then if we add 3 to 0, that gives us 3. The absolute value of 1 is 1, and then if we add 3 to that, we get 4. Same thing with 2. The absolute value of 2 is 2, plus 3 gives me 5. The absolute value of negative 1 is positive 1, plus 3 gives me 4. And then the absolute value of negative 2 is 2. Add 3 to that, and that would be 5. So if we were to actually sketch the graph here, 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, and a 1. Okay, if we plot these points, we got 0, 3. We had 1, 4. We had 2, 5. Negative 1, 4, and negative 2, 5. We have our new, our new function here. Looks like that. Okay, so remember, the original one was down here. Now we've just slid everything 3 units up. Hopefully you can see that. Okay, the last thing here to describe the domain and range. So remember, domain is x values. Okay, domain is x values. Let's see, we'll do this in blue. So the domain and then the range. The domain. There's no x value that we could come up with to plug in here that doesn't have an absolute value. Every number we could come up with is some distance away from 0, okay? And that's going to be true for every absolute value function. So every time we're working with absolute value functions and it asks for the domain, the answer is going to be all real numbers. And that's how you shorthand all real numbers. I'll write it out. All real numbers, okay? The shorthand is, it's an R with a vertical line through it. So a capital R here, and then just a vertical line through it. The range, those are all the y values. We're looking at the purple function here. If you look, it's going upwards in both directions, but it's got this point down here at the vertex where it bottoms out. The y value of that point is 3. And we have a closed circle here. It's a dot. We show that we can use the y value of 3. So we can say that the y's are all greater than or equal to 3. That is the range for this particular function. Every absolute value function is going to have a domain of all real numbers. This is not going to change. The range might change a little bit, so it's going to depend on where the vertex is and which direction the graph opens. Okay, and we'll see some examples where it's less than or equal to, and it might be 0 as well. So we'll keep working through it, and we'll see some different examples. All right, number 2, h of x is equal to the absolute value of x minus 2. We're keeping the same direction. So the first thing we did was describe the transformation. Now, if you look, the plus 2 is on the inside, and the rules change whether we have function notation or we're just looking at the actual new function. Okay, so we're adding and subtracting again, so it's a translation. Translation. This is going to be 2 units. And if it's plus 2, then that means, remember it's horizontal, so it's going to be backwards because we're doing it directly to x. It's directly to x, so it's going to be horizontal. Translation 2 units, this is going to be to the left. Remember, directions are always backwards when we think about horizontal translations. The directions are always opposite. Okay, so we're going 2 units to the left. So when I come up with my x's and y's, x, y, 1, 2, 3, 4, leaves me 5 spaces. Normally, this vertex, the vertex here would be 0. But if I go 2 units left on the number line, what that puts me at is negative 2. So I'm going to put negative 2 there in the middle of my xy table. And then I'll come up with 2 x values that way, 2 more x values to the left, and we'll come up with some y values. So to find the y values, we can just take these x values, put them into our function, and come up with, see what we get. So if we plug in negative 2 plus 2 is 0, and the absolute value of 0 is 0. Okay? Let's think about negative 1. Negative 1 plus 2 is 1, positive 1, and the absolute value of positive 1 is positive 1. If we plug in 0, 0 plus 2 is 2. The absolute value of that is still 2. Negative 3 plus 2 is negative 1, and the absolute value of negative 1 is 1. And negative 4 plus 2 is negative 2, and then the absolute value of negative 2 is positive 2. Okay, so we have our x's and y's. Let's go ahead and sketch our picture. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Okay, so we have negative 2, 0 right here. Negative 1, 1 is there. 0, 2 is there. Negative 3, 1 is there. And negative 4, negative 2 is right there. Okay, so we've graphed the function. We've described the transformation. The last thing we need to do is describe the domain and range. So the domain, the range, the domain. Every problem with absolute value is going to be all real numbers. There's no x value we could put in there that wouldn't have an absolute value. The range, we got to look at the y values. This is our bottoming out point. This would be a y value of 0. And we can obviously use 0 because we have a point that's got a y value of 0. So the range here for this one is going to be y is greater than or equal to 0. We're opening upwards. Now, let's just say we had an example where the graph went this direction. Okay, the domain is still all real numbers. The range, though, would be y less than or equal to 0 because we're going downwards. 0 would be the maximum, and we want everything below that. But that's just kind of a side note. In case you get something that opens downward, the range does change a little bit. All right, moving on. Vertical stretches and shrinks, and also reflections. So we're focusing on y equals a times f of x, thinking back to the notation from section 3.6. Okay, if a, remember, just as a side note, whoops, one too many back buttons, if a is greater than 1, it's a stretch. If, let me come up with, let's still use blue. If a is between 0 and 1, that is a shrink. And if a is negative, that is a reflection in the x-axis. We're going from like quadrant 1 to quadrant 4. Okay? So number 1 here, graph the function, describe the transformation, and state the domain and range. So the directions aren't changing. So this, I can't type fractions in this program, so g of x is equal to 1/2 absolute value of x. And we're still assuming that f of x is the absolute value of x. We're still using the parent function. Okay? We're now just kind of changing things. Again, we could rewrite this as g of x is equal to 1/2 times f of x, because remember the absolute value of x is equal to f of x, according to that. Okay, so we can think, let's go right to describe the transformation. We'll keep the same colors. Describe the transformation is in red. Now, this 1/2 is on the outside of the function. It's not with x, so that makes it vertical. And we're multiplying, we're not adding or subtracting, so it's not a translation, it's vertical, which means we're going to have a vertical, well, something. We'll leave that blank for now. By a factor. Well, if it's vertical, this number right here is the factor. Okay, so this is a factor of 1/2. Now, 1/2 falls in here. It's between 0 and 1, which makes it a shrink. This is a vertical shrink by a factor of 1/2. Okay, the second part, and that's really the only transformation, so that we can move on to the second part, graph the function, which, as it's written, is the first part. Okay, so we're going to take x, we're going to take y. We're not sliding it anywhere, so our x values are going to go back to the old ones, -2, -1, 0, 1, and 2. Okay, so now we need to take these x values, plug them in, and then multiply them by 1/2 or divide them by 2. Either one is fine. So let's go ahead and do that. So we take the absolute value of 0, which is still 0. 0 times 1/2, or half of 0 is still 0. This one's not going to change. Okay? Let's see. Absolute value of 1 is 1. Half of 1 is, that's 1/2. Okay? What I hope you're noticing is that we can reflect this. These are going to be the same. They have that nice little reflection, that symmetry to it, that this is going to be also 1/2, because 1/2 of, or the absolute value of -1 is 1, and then it's the same thing. Half of 1 is 1/2. Okay, so if we think the absolute value of 2, the absolute value of 2 is 2. Half of 2 is 1. Okay, and then the same thing with the -2. Absolute value of -2 is 2, times 1/2 is also 1. So we can go ahead and sketch our picture. This one doesn't need to be nearly as tall. Okay, and I'm going to erase this one, Fill that in, just make it a little more even. So we got 0, 0. We've got negative 1, 1/2. We have 2, negative 2, 1, 1, 1/2, and 2, 1. So this one definitely much flatter, much wider than the two we saw previously. All right, so we talked about we've described the transformation, we've graphed the function, now we need to state the domain and range. For the domain, remember, every time it is the same. It is all real numbers. You can pick any x value and it's going to work. The range, well, here's our bottoming out point. That's a y value of 0. So y, 0. Can we use 0? Yes, because we've got a point that has 0, and we're going upwards. Okay, we're going up, so that's greater than or equal to 0. Okay, so the domain, all real numbers, the range, y greater than or equal to 0. Let's try one more. H of x is equal to negative 2x. We're going to keep the same rules. We're going to describe the transformation, we're going to graph it, and then we're going to state the domain and range. So the transformation, we've got a negative 2 out front. So since it's out front, it's not directly to x. That means it's vertical. Let's focus on the 2 part, because the negative is a different transformation. So we got a vertical something by a factor of, if it's vertical, that number is the factor. Okay, and if it's bigger than 1, like this one is, this is a stretch. So this one is probably going to be a little taller or a little more narrow than the ones we've seen so far. That takes care of the 2. Now the negative, again, it's on the outside of the function. It's not directly to x, which means, and anytime it's negative, that means it's going to be a reflection, and it's a reflection in the x-axis. Okay, we're going from quadrant 1 down to quadrant 4, quadrant 2 to quadrant 3, or the other way around, 3 to 2, 4 to 1. We're going up and down. We cross the x-axis. Those are the only two, that's the only number, that's the only transformation we have. It's actually 2 of them, vertical stretch and a reflection. But let's go ahead and figure out our ordered pairs. So x, y, 1, 2, 3, 4 gives us 5 spaces. We're not sliding it, we're not translating it anywhere. So I'm going to keep my x values the same, negative 2, negative 1, 0, 1, and 2. To find the y values, again, just take these x's, plug them in. So the absolute value of 0 is 0, and then 0 times negative 2 is still 0. The absolute value of negative 1 is, the absolute value of positive 1. We plug it back in here. That's 1. And then negative 2 times 1 is negative 2. Same thing with the 2. Absolute value of 2 is 2 times negative 2 is negative 4. Again, same thing on the other side. Negative 2 and negative 4. The rules are still the same. Plug them in, multiply it out. Hopefully you're starting to see that there's some reflecting going on here that you wouldn't necessarily have to find all 5 points to get these numbers. You can find these 2 and reflect it over as long as your vertex is in the middle. All right, so let's go ahead and graph. We've got our ordered pairs. So now our y values are a little bigger this time. So we got 1, 1, 2, 1, 2, 1, 2, 3, 4. And our y values are also negative. So we got 0, 0. We've got negative 1, negative 2. We have negative 2, negative 4. 1, negative 2, and 2, negative 2. So this one, hopefully, you can see is a little more narrow. It's a little steeper, okay? But there's our graph. So now let's describe the domain and range. The domain, every time, all real numbers. We don't even have to think about that. The range, this time we've got a peak. We don't have a bottoming out point. We have a maxing out point. That maxing out y value is 0. So it's going to have y 0. It's going to be or equal to because we use it. And this time we're going below it. We're going down. Down on the y-axis is less than. So our range in this one is y is less than or equal to 0. So that's a basic introduction to absolute value functions. This is part 1. There's going to be a second video dealing with multiple transformations, and it gets a little more complex. But hopefully this is a good introduction and we can keep moving forward.